What's up, everybody? Welcome to Chapter 3. This is Section 3.1, Graphing Quadratic Functions. And so there's some things we can review. We've already seen intercepts of quadratic functions. And when I say quadratic, I just mean like things that are squared. X squared, not x cubed, not x to the fourth, but just x to the second power. We've already seen these kinds of intercepts, and we've already seen max and min, and domain and range and transformation. The thing that's new today is a vertex form of a quadratic function. It would look like this. You can take any quadratic function you want and turn it into this format. And the great thing about this is that you can immediately read the h comma k. You can find the vertex very quickly. That's why it's called vertex form. So, and you can also see that the vertical dilation is a when you see that. So for example, if I see f of x is equal to x minus 1 squared plus 2, then you can immediately read from that that the vertical dilation is 1, right? There's a 1 right here. And then the whole thing has been shifted 1 unit to the right, horizontally shifted 1 and vertically shifted 2. Remember that there's a formula x minus h, and so therefore, because the formula expects subtraction, then this number over here is positive 1. I'm not going to make you do the table because there it is. I hope you're all experts at doing graphing tables by now, and it would be right here, so you can plot those points. But the one thing that is new today is that you can see there's a vertical line of symmetry right here at x equals 1. So here are some things that we can identify. We can identify that the domain is all real numbers. That the collection of all x values is all real numbers, but the range is only the lowest number for the lowest y value is 2, and it goes up to infinity. The y-intercept right here is 3. The minimum is the function itself has a minimum of 2. That's the lowest value it can reach, and where? When x is equal to 1. There is no max. There's a horizontal shift of 1, a vertical shift of 2. It is decreasing from negative infinity all the way up to 1. These are x values. From the x value of negative infinity, which is not really a value, but from negative infinity all the way up to 1, it's decreasing. And then it's increasing from when x is equal to 1 all the way up to positive infinity. The vertex is at the location 1, 2. There's a line of symmetry, x equals 1, and it opens upward, meaning, boom, it looks like a U and not an N over here. Here, this is vertex form. The vertex form of this, it's already in vertex form, and because of that, we can read this is not a equals 1. This is a equals negative 2. Because there's a negative 2 right there. There's a vertical dilation of negative 2. And then you can see the k value is 4. But the h value is negative 3. You see plus, and it's actually the opposite. It's negative 3. You all know how to do graphing tables. I won't make you do that in the notes again because you can do it by hand if you needed to. But you can see that the domain is all reals. The range is from negative infinity up to 4. That's why the highest y value is 4. It has a y-intercept of negative 14 and an x-intercept of negative 4.4 right here. Oh, there's 2 of them. Yeah, and negative 1.5. You can see the x-intercepts. There's 2 right here. Although there were no x-intercepts over here, we've got x-intercepts here. It has a maximum of 4 at negative 3, and there is no minimum. It's a horizontal shift of negative 3, vertical shift of 4, and a vertical dilation of negative 2. It is increasing from the x values of negative infinity up to negative 3, and the x values from negative 3 to positive infinity, it is increasing. No, it is not. It is not increasing. It is in fact decreasing. Whew. Glad I caught that one. Vertex is at negative 3, 4, and the line of symmetry is x equals negative 3. It opens downward. As you can see, it looks like an N, not a U. It's been flipped vertically. Here, you can see f of x is equal to and now you might ask, Mr. Bergman, how do you know to graph this at negative? How do you know to put negative 3 right here in the middle? Well, that's because we knew that the h is equal to negative 3, and so the h value it's going to give me the vertex. This middle row right here it represents the vertex, negative 3, 4. So if you know what the h value is, then just put it right there in the middle. Put a few points on one side and a few points on the other, and then you'll be able to graph the vertex very well. If you don't do that, then you're just going to get a whole bunch of what looks like almost straight points in a line, kind of not at the vertex of the parabola. Now here we go. We got f of x is equal to 2x squared plus 4x minus 5. And that is not in vertex form. So we're like, how are we going to know what values to choose, what x values to choose that will conveniently graph what we can see for the parabola? There's a formula we got for that, and if it's in the general form of a quadratic function, that is ax squared plus bx plus c, which is actually a pretty handy formula to have for other purposes. But if we're trying to find out where the vertex is, it's not helpful. There's a little trick you can use, h equals negative b over 2a, and I will tell you where that formula comes from later. We'll actually derive it, we'll prove it, we'll show it. But for right now, you can just accept it. H is equal to negative b over 2a. So you take that a value and that b value, and you put it in here, and then that's how you can figure out where to go. So the a value is 2, the b value is 4. The b value is, so that'd be negative 4 over 2 times 2, which is just negative 1. And that's why we can put negative 1 right here in the middle of the table and crank out the y value as negative 7. You can crank out all these values, and you can see the symmetry, negative 7, negative 5, negative 5, 1, 1, and plot them, and there it is. Line of symmetry, oh yeah, here it is, general form. A equals B, A equals 2, B equals 4, C equals negative 5. Plug them in, you get H is equal to negative 1. Domain, again, is all reals. The range, the collection of all the y values goes from negative 7, that's the lowest y value, up to positive infinity. It has a y-intercept of negative 5, an x-intercept of negative 2, and also 0, and has a minimum of negative 7, where at x equals negative 1. There's no maximum value of this function. It just keeps on increasing forever and ever and ever. It has a horizontal shift of negative 1, and a vertical shift of negative 7, and a vertical dilation of 2. We knew that because we can get this information that it's from the vertex negative 1, negative 7. This is basically h, and this is k, and then the vertical dilation is going to be 2 because a equals 2. It is decreasing from negative infinity all the way up to x equals negative 1. It is increasing from negative 1 up to positive infinity. It has a vertex at negative 1, comma negative 7, line of symmetry at x equals negative 1, and it opens upward. Oops. All right, you see all my notifications. That's fine. All right. Here again, general form is it's in ax squared plus bx plus c form, which is great for some things, but for the vertex, we gotta use our little trick. We know that a equals 3, b equals negative 2, and c equals 1. So plug that in. We get h is equal to negative 2 over 2 times 3, which is the same thing as positive 1/3. So you can put 1/3 right here. And I know it's a fraction, but it's okay. You can, especially if you've got a calculator, you can just calculate this out, or just do it by hand. Anyway, this turns out to be 2/3, and you don't have to put fractions in all of them. It's just here's where the vertex is, and you've got there's no I don't really have to have symmetry on either side. You know, it's fine. You just put a couple of points and connect them, and you're done. The domain is all reals. The range is from the lowest y value is 2/3, and it goes up to positive infinity. The y-intercept is 1 right here, and you can see this row corresponds to the y-intercept 0, comma 1. The minimum value of the function is negative 7. No, it's not. Minimum value of the function is 2/3. Dang, I'm off my game. 2/3. When x is equal to 1/3. There is no maximum value. There is... Ooh, no, it went away. Minimum is 1/3. Minimum value is 2/3. When x is equal to 1/3. Vertical shift of 2/3, vertical dilation of 3. It's decreasing from negative infinity up to 1/3. It's increasing from 1/3 up to positive infinity. Vertex, there it is. Line of symmetry is x equals 1/3, and you can see it opens upward. Oh, this is my favorite absolute topic to teach and pronounce. It's pronounced A-rock. Everyone say A-rock for me. Boom. That's average rate of change. AROC. When you come into class tomorrow, you can give me a big A-rock. It's basically the slope formula, but applied not to straight lines, but to curves. Just to give you a visual, you can't take the slope between this point and this point unless you just pretend there's like a dotted line, a straight line in between the two. This is curved. It's a wonky data. It's not linear at all. But if you wanted to apply the slope formula to it, if you wanted to find not the slope, but the average rate of change, like if you were going to smooth all this out and pretend it was a straight line and use the slope formula, then that would be the average rate of change. It's basically the slope between 2 points that are on some sort of a curve. For example, the table shows the number of students who took the ACT between 2011 and 2015. During that time, there was a big increase, but not since then. What is the average rate of change in the number of students taking the ACT from 2011 to 2015? You can ignore all of these numbers right here. Everything in the middle does not matter whatsoever. You take the first value, you take the last value for the input and the output. For the x value, like you just need x1, which is here, and x2, which is here, y1, which is here, and y2, which is here. And then you apply the slope formula. So y2 minus y1 over x2 minus x1. You get that, crank it out, and boom. On average, between those 5 years, there were 75,331 students per year, and that is an average rate of change. That's numerically right here. You can see that on the table. Example 2, the graph shows the cost of the Super Bowl ad over time. On average, how much does the cost increase every year? That is, what is the average rate of change from 1967 to 2012? It's a whole bunch of years. That's 45 years. You can see that it started down here and it went up here. And if you're going to smooth this curve out into basically a straight line, it's not smooth all the data out into basically a straight line, then that's what it would look like. You take the first x value, take the last x value. That's 1967 to 2012. You take the y1, the y2, and you subtract. And so basically, on average, it was increasing $1,666.67 per year. Determine the so I hope talking about it in terms of like real life context helps to understand what average rate of change are. But you don't really need a word problem to do average rate of change. You can just think, Alex.com could just give you some random function and some random interval, and you got to apply what's going on. I find it helps if you're doing it by hand to put out an input-output table. So here are the x values. This is going to be x1. This is x2. And then you can using an input-output table, you can calculate the y1 and y2. And using the table just helps you, get organized. Anytime you can organize your information, it's just going to be a lot better. So especially when math gets hard, the best math students just get organized, and this is how you organize your work. So you can see x1, x2, y1, y2, and you're much less likely to make a mistake because you're organized. You write out that formula, m is equal to y2 minus y1 over x2 minus x1, and plug in your numbers. You get 80 over 8 and equals 10. There's no units on that because it's not a word problem. The average rate of change is 10. That's the slope. So here it is. The key concept is that the average rate of change of a function is equal to f of b minus f of a over b minus a. This is the same structure of the slope formula. It's just put in terms of an interval from a to b. So there it is, y'all. Thanks for playing. I'll see you next time. Take care.